Hey everyone, let's look at section 6.2, the binomial distribution. Now that we know a little bit about random variables, let's discuss the most important discrete distribution, the binomial distribution. Now before we can define that, we have to define a binomial experiment. Is an experiment, which means we're doing something, right? Something is happening. And in the case of a binomial experiment, there is a fixed number of trials, which we denote with n. N is the number of trials. All trials are independent. Remember that term from the previous section? And under identical conditions. So effectively, you're doing the same trial n times. Each trial has exactly two outcomes: success and failure. And all trials have the same probability of success and failure, where the probability of success is p, and so the probability of failure has to be 1 minus p, right? Because success and failure are complements. And the key thing we're looking at with the binomial experiments is to count the number of successes out of n trials, or to find the probability of getting a certain number of successes given n trials. So that should be out of. All right, so let's consider a couple of examples and see whether they're really binomial experiments or not. And in particular, the way the book phrases it is they say, determine whether the random variable x has a binomial distribution. Effectively, is this a binomial experiment? So let's see. 10 students are chosen from a class of 25 students, and x is the number who got an A in the class. There is a fixed number of trials, right? 10, choosing a student, right? All trials are independent? Well, no, they're not, because when you choose the first student out of 25, the sample pool is now down to 24, and then you choose another one out of 24. That's not quite the same as choosing one out of 25. So, no, because trials, right, which is to say choosing students, are not independent. Okay? 10 students are chosen from 300 students, right? Let x be the number who got an A in the class. Well, technically speaking, the trials still are not independent. However, the book does have a little note that says, well, if your sample is less than a certain percentage of the population, then it's okay. I believe it's 5% is what it is. So since 10 out of 300, which is 1 out of 30, is less than 0.05, the trials are considered independent. Again, technically they're not, but effectively they are. So, yes, this one's okay. This one wasn't. I'll make this one's an X, and this one's okay, right? Coin is tossed 7 times. Let x be the number of heads obtained. Absolutely. Yes, that's the standard example. Doesn't need to be a fair coin, by the way. But note that there's a fixed number of trials, 7, right? All trials are independent and identical, right? We can assume each coin flip is the same as the one before. There's only 2 options, success and failure, right? Heads or not heads. Probability of success is 50%, failure 50%, right? So we're good. A die is tossed 3 times. Let x be the sum of the 3 trials. Well, that's not going to be okay, right? That's not binomial because there are more than 2 outcomes. Right? There are, right, 3 times the sum of the 3, or I guess, yeah, there are 6 outcomes per time, right? And x has, I guess, 15 possible outcomes, or 16 possible outcomes, so definitely not. Let's see. A coin is tossed until a head appears. No for this one as well, because the number of trials is not fixed. This is actually called the negative binomial distribution. So, let's see. A random sample of 250 voters chosen from a list of 10,000. X is the number who support, and that one is also good. Yes, right? Since 250 out of 10,000, let's see, that's 25 out of 1,000, whatever. It's going to be less than 0.05. The trials, effectively choosing a sample of voters, choosing, right, each voter, are effectively independent. All right. So one way to look at a binomial experiment, right, is using a baseball analogy. So look at baseball. Now, if you don't know baseball, the basic idea is that the pitcher throws the ball to the batter, and the batter has to try to hit the ball. Now, either the batter gets a hit, a success, or makes an out, failure. Okay? So, a binomial experiment in baseball is an at-bat, or AB. Or I guess I should say, binomial experiment in baseball is not even just one at bat. That's a trial. Binomial experiment is the set of at bats, which we denote by AB, per game for a single hitter. Each at-bat is a trial. The hitter's batting average, which equals hits per at-bats, is the probability of a success. And the trials are effectively independent and under identical conditions. Right, the trials, which are to say the at-bats, are independent and identical. Again, not literally, but pretty much. And the only outcomes are hit, success, or out, failure. Okay? The binomial distribution is the distribution of successes given an experiment with a fixed number of trials and a fixed probability of success. Now, it turns out you don't need to know this, but just in case you care, the probability of R successes in N trials equals, and it turns out it's something called N choose R times P to the R times 1 minus P to the N minus R. And in case you're wondering what that means, it turns out it's N factorial times R factorial times N minus R factorial, all times P to the R times 1 minus P to the... You can just go ahead and skip this, right? We don't need to know this. I just want to point out that this is a thing. When we use Minitab, this is what Minitab is doing. If this does interest you, then you should take discrete mathematics. You learn all about this stuff. Or combinatorics. It's lots of fun. Anyway, thanks to fact 1, we can attempt to determine a player's success at the plate using the binomial distribution, right? We have a very nice formula for for determining the number of successes given the fixed number of trials and the fixed probability of success. Right. Now, remember that the expected value of a variable in general winds up being this, right? This kind of complicated formula, standard deviation. Actually, expected value might also be written as mu x. Standard deviation is written also like this. We don't need to worry about those formulas right now because it turns out the expected value of a binomial distribution is mu of x, or the expected value of x, equals n times p. Very, very nice and straightforward. And the standard deviation winds up being the square root of n times p times 1 minus p. Very nice, simple formulas. Okay. So let's test out this whole binomial distribution in baseball thing. And it'll give us a chance to use Minitab, right? So we're looking at a 2020, this is what another class chose, so I'm going to use this example. Colton Wong, I think he was a player on the Orioles in 2022, had a batting average of 251 that year. Assume Wong's 4 at-bats per game. Again, this is a bit of an assumption. He sometimes had more than 4 at-bats. Constituted a binomial experiment. Okay. So that's our n, right? N equals 4. So let P, his probability of success, be 251. We can use the binomial distribution to try to predict the number of 0, 1, 2, 3, and 4 hit games that he had, assuming he had 4 at-bats per game, assuming that his batting average is 251. Now, again, both of these are a bit of an assumption. His batting ability likely changed throughout the year. His at-bats weren't perfectly independent or identical. There were different pitchers, etc. But still, we're gonna see how effective the binomial distribution was. So anyway, let's just let's take a look, right? Let's see the probability that Wong got 0 hits in a game. Well, we could write out that big formula up here, or what we could do, might be a little bit shorter, is use Minitab. Calc, probability distributions, probability density function, right? For I'm put a single value, our value at this point is going to be 0. Make sure your distribution is set at binomial. Number of trials in this case is going to be 4. The event probability is going to be 251, right? The idea here is that he has 4 at-bats per game, and we're seeing what's the likelihood that he doesn't succeed in any of them in a single game. Turns out it's about 31% or so. So I'll just say 0.31. All right, and so we can do similar things for the probability of 1 hit, or 2 hits per game, or that he got 3 hits in a game, or even 4 hits in a game. Right, and let's quickly use Minitab to find out our answer, right? So we go to Calc, probability distributions, density function, and the only thing we're changing is that 0 becomes a 1. Oh, look, 42% of the time, okay? So he was a bit more likely, to get 1 hit per game than he was to get 0 hits per game. All right, what about 2 hits? Well, again, here. Change the 1 to a 2, and we're good. And we get about 21%. And so you see how we're creating our probability distribution, our binomial probability distribution. Right, let's take a look at 3 hits. Calc here, here. Change it to 3. About 5%. All right, we're going to round to the nearest hundredth. And then last but not least, what's the probability he goes 4 for 4 with 4 hits per game? Oof. 0.004. I guess I'll go out one more digit in this case. Just because otherwise it would be about 0, right? Right. All right, so we have our answer, right? Now, let's compare this to how he actually did, right? All right, so just to be clear, this was calc, probability, distributions, and then density function. I think it may have been, yeah. Okay, so that's how we did it. Okay, now anyway, let's look at how he actually did. So Wong, it turns out, played in 134 games. So the expected number of 0-hit games is going to equal 134, right? Remember that remembering that EX equals N times P, is going to wind up being 134 times 0.31. His expected number of 1-hit games is going to equal 134 times 0.42, right? And you can just sort of keep doing this for all the others. Oh, I keep messing that up, right? 134 times 0.004, right? Now let's see what we get when we do this out, okay? All right, we can just use, we don't need a high-tech calculator. You could use Minitab, but I think we can just get away with this. Right, this is 41.5. Note that I'm not going to round to the nearest game. I just want to keep it the way it is. It's okay that we're not getting perfectly accurate results, right? So for this, it's going to be 56.2. 28.1. 6.7. And then 0.5. Okay, so let's interpret these results really quickly, okay? This is saying that given that he has a 251 average and played in 134 games, we would expect Colton Wong to have about 41 to 42 0-hit games, right? We would expect him to have about 56 1-hit games, 28 2-hit games, 6 to 7 3-hit games, and maybe no or 1 4-hit games, 0, 1, 4 games. Now, it turns out that this is what we wound up getting. Right? So this right here was the number of expected. games, and this is what was observed. So not the most perfect prediction, right? Notice that here we're a little bit off, right? But otherwise, we were pretty good. This is a pretty good prediction. This was, again, a little bit off, but nothing terrible. This was pretty exact, and this was pretty exact, right? So really, this is the only prediction that wasn't quite right. We sort of underestimated his number of zero-hit games and slightly overestimated everything else. Okay? So this is sort of a nice example of using the binomial distribution to model a situation. Right? Now, one more example. I'll do this very quickly. Use Minitab to calculate the probability of at least 6 successes in a binomial experiment. Right? Now, what this means... i.e., let n equal 15 and p, the probability of success, equals 0.3. What's the probability that we complete 15 trials and get 0, 1, 2, that we get 6, 7, 8, 9, 10, 11, 12, 13, 14, or 15 successes, right? At least 6 successes. So the probability of at least 6 successes equals. Now, the way that we have to do this, we have to be a little bit clever. This is 1 minus the probability of, at most, 5 successes. Do you see that? Think about why that's the case, right? It has to do with complements. All right? So anyway, that's going to be 1 minus, well, how are we going to do that? Well, we could find separately the probability of 0, 1, 2, 3, 4, and 5 successes, or we can go into Minitab and do calc, probability distributions, cumulative distribution function. All right, value is 6. Make sure the distribution is set at binomial. Number of trials is 15. Event probability is 3. Oh, wait, no, actually, sorry. We want this value to be 5. Right? And note that this gives us the probability that x is at most 5. So 1 minus 0.72, which is about 0.28. Okay. So the probability that we get 6 or more successes with only a 30% success rate is about 0.28. And that's what we've got.